A circle is a set of points that is equidistant from a center point. So I have a circle on the screen here. Let's say I introduce center point A. The distance from A to any point on the circle, let's say I call this point B, or to another point that I call C, by definition will be the same length. So AB is congruent to AC. That segment that connects a point on the circle to the center is what we call the radius. And it is the segment that defines the circle. So once I change the radius of a circle, I have a new circle. It is no longer congruent to whatever I started with as a radius length. If you're familiar with area formulas and circumference formulas, you can see that those are solely dependent on the length of the radius, whether it's pi r squared for area or 2 pi r for circumference. So the radius is a segment that connects the center to a point on the circle. And again, it is what defines the circle. It is always the same length no matter what point on the circle I am drawing that segment to from the center. Now, another type of line that's going to be involved with the circle would be a segment that connects any 2 points on the circle. So let's say I have D and E here. When I introduce a segment that connects those 2 points, that is what we call a chord. So a segment that connects any 2 points on the circle. Now, what is the longest possible chord that we could draw? Well, it would have to be connecting 2 points with a segment that passes through the center. So FG is a chord, and it is the longest chord. And there's a special name for that chord, and we call that the diameter. Now, because it passes through the center, and we know that the distance from the center to a point on the circle represents a radius length, we now have a relationship between radius and diameter. We know that the diameter is composed of 2 radii. So there's the relationship diameter is equal to 2 times the radius, or by manipulating that equation, we know the radius should be half the diameter. So those are the 3 main segments that we're concerned with: radius, chord, and diameter. Now, what about lines? So if we extend beyond the boundary of the circle with, say, a line that intersects a circle at 2 points, H and I. So we can see segment HI is a chord. So imagine if we just extend beyond in either direction. That line is called a secant line. So secant means to cut. And you can see that that makes sense and is appropriate for that line because we are cutting the circle. So a line that passes through 2 points. And if we're working with straight lines only, then 2 points is the most that we could intersect. Now, just some notation here. When I want to write the notation for the secant line HI, just recall that we want to introduce arrows for the line that's over the top of those 2 letters. The 2 letters are going to distinguish what line we're talking about when there's several lines involved. And if I don't have the 2 arrows on there, and it's just a little line, again, with no arrows, then that means we're talking about the segment. So this would be for the secant line up top. And then down below here, that's what I would write if I was wanted to talk about chord HI, because a chord is a segment. So just be aware of that notation difference when looking at various problems. That way you can differentiate between what the problem is actually talking about or referring to. Now, at most, we can intersect 2 points with a line. We could intersect 0 points if we wanted to. We could just draw a line in space on the exterior of the circle. But we want to know about lines that are involved with the circle, so I could intersect the circle at just 1 point. And we call that a tangent line. So tangent meaning to touch. And that point of intersection is what we call the point of tangency. So a line that passes through 1 point. And there are the 5 types of lines and segments that you want to be familiar with that are involved with the circle and what they mean and how they're related in some cases. So now that we've introduced those, let's look at some properties or relationships between some of these lines and segments. One theorem says that if we have a tangent line to the circle, there exists a radius that runs perpendicular to that tangent line. And for that to happen, that radius must extend from the center to none other than the point of tangency. So when I see a radius that is connecting the center to a point of tangency, we know that that radius is running perpendicular to that tangent line. So the theorem says, if we have a tangent line to the circle, there is a radius from the center to the point of tangency that runs perpendicular to that tangent line. And the converse of that is if we see a line running perpendicular to a tangent line, we know that that line represents a radius. Now, if we see this scenario, we know that this line is tangent for the following reason. We know the only point of intersection is at point B, because if I were to draw a line from point A to any other point on this tangent line, so I'm marking these in blue, no matter where I intersect the tangent line, those points of intersection are always on the exterior of the circle, which would indicate that it is only made one point of intersection with the circle, and therefore it is tangent. And the reason why they're all on the exterior for sure is because if we know A to B runs perpendicular to that line, those blue lines I've introduced, you can see that there are these right triangles that form. And those blue lines always happen to represent the hypotenuse of the right triangle. So if the vertical leg, in this case, the way it's standing, is a radius, that leg length is always less than the hypotenuse length, and therefore, those points must be on the exterior of the circle because the hypotenuse is greater than the radius, so it extends beyond the boundary of the circle. So a neat little explanation as to why, if we see a line running perpendicular to a tangent line, or what we think it should be a tangent line, we know for sure it is tangent for that reasoning. Now, what else do we know from that fact? So we know when we have a tangent line, there's a radius that runs perpendicular to it. Let's say I introduce a point on the exterior of the circle. If I draw a line that runs tangent to the circle that connects to that exterior point, draw one that's a little more straight than that. There we go. And I draw another line that's tangent to the circle and also connects to that exterior point. What must be true about those two lines? So let's say this is one point of tangency. Let's call this A. We'll call this point out here B. We'll call this point of tangency C, and this point of tangency D. So we have BC runs tangent to the circle, and DB runs tangent to the circle. Well, it actually must be true that this is congruent to this, and here's why. We know there's a radius that runs perpendicular to that tangent line. If I draw a line that connects A to B, that has just created two right triangles, and that blue line represents the hypotenuse for both of those right triangles. So both of those right triangles are sharing a hypotenuse, and the leg for each one, or one of the legs I should say, is a radius length, and the radius is always the same length. So by the hypotenuse leg theorem, both of these triangles are congruent, and therefore, if I have congruent triangles, well, corresponding parts on the triangle must be congruent, and that is why BC is congruent to BD. So recognize tangent lines that meet at a common exterior point must be congruent in length from the exterior point to their points of tangency. Another thing to be aware of is if we have some center point and there's a chord on the circle, there is one radius that we could draw that runs perpendicular to this chord. There's only one option. And when I introduce that radius, that chord gets bisected. And the reason why is if I introduce two more radii from A to C and A to B, we know this is congruent to this because all radii are the same length. We also know that the two triangles now formed, so this intersection we'll call point D, share a leg from A to D, right? A to D is shared amongst the two. So now we can see we have two right triangles that have congruent hypotenuse lengths, and they share a leg. So by hypotenuse leg, these two triangles are congruent, and therefore the corresponding parts are congruent. So this piece, B to D, should be congruent C to D, and therefore we now know that when a radius runs perpendicular to a chord, the chord gets bisected. Okay, so that's the theorem you want to know. Radius runs perpendicular to the chord gets bisected. In converse, if you see a bisected chord, you know the line that is bisecting that chord represents a radius. Now, me introducing these radii is a technique that you're going to want to be able to draw in on your own in the event a problem asks you to find the length of BC when you have a radius length. So for instance, let's say we're asked to find the length of BC. What we're going to say to ourselves is we know that A to E represents a radius because we see that it runs perpendicular to the chord by that theorem. Now, let's say they give us information that AE is equal to, say, 6 and DE is equal to 2. So we know this little piece is 2. And therefore, this must be 4. So AD must be 4 if the whole thing's 6. Now, how can we find the length of the chord BC? Well, here's what we can do. Again, so what I was saying is you can draw in your own radius because you know from center to any point on the circle is always the same length. So you know that this is 6. Then you could do Pythagorean theorem to get CD. And if you know CD, you know BC because all you have to do is double it. So drawing in your own lines is a valuable problem-solving technique when it comes to circles, whether you draw in your own chord or your own radius or your own diameter or things of that nature. So there is a video on different types of lines, relationships between lines, say tangents and radii or radii and chords that you want to be familiar with.